This is chapter 1, real numbers. In class 9 we have also learnt about real numbers. Real numbers are the group of numbers that include rational as well as irrational numbers. Rational numbers are the one that can be written in the form of P by Q. So now we are going to learn the properties of real numbers in this chapter. The first property is the Euclid's division lemma. Euclid's division lemma. What is the meaning of the word lemma? Lemma is a strange word. I think I have not heard this properly. That time I saw the dictionary. The dictionary says that lemma means a proven statement that is used to prove something else. So there is a statement that is already proved by somebody else, and now we are using that to prove something else. So what does this Euclid's division lemma say? Euclid's division lemma says that for any two integers a and b, there exists two more integers q and r such that a is equal to bq plus r, where r is some integer that is less than or equal to 0, that is greater than or equal to 0 and less than this divisor, which is also called as b here now. This is the Euclid's division lemma. So based on this we have to prove some now questions. Now we are going to use Euclid's division lemma just to find the HCF, that is the highest common factor of two numbers, say a and b. So what is the algorithm? Algorithm is a series of steps that you need to follow to find out this, that is the HCF in this case. So first you are going to use the Euclid's division lemma. Using Euclid's division lemma, you need to find q and r such that a is equal to bq plus r, where r is in between 0 and b. Step 2. In the first step you have found out that r is in between b and 0. So there are different cases that are coming here. Either r can be 0 or r can be some other integer. So if r is equal to 0, in the case when r is equal to 0, then b is the HCF of a and b. That is the first case. In the second case, that means that r is not equal to 0. If r is not equal to 0, then apply Euclid's division lemma to b and r. In step 3, now you are finding out again some term like q and r in this case, until you need to continue that process again and again. Continue until remainder is 0. In that case, the divisor, what do you call the divisor here? Divisor is the b. The b at that stage is the HCF of given things, that is A and B. Yes. Now we are going to have an example. For having an example, I am going to take, you need to find the HCF of you need to find the HCF of 867. Find the HCF of 867 and 255. 255. So how do you need to find this? Now we have the numbers. This is A and this is B. So you need to write it in the form of A is equal to BQ plus R now. So 867 is equal to 255 into something. I need to enter something, and here one more. So for this I need to divide 867 divided by 255. That's a very big number, so I'm just trying to multiply it such that I get a number just less than 865. So 255, approximately 250. 250 3 times is 750. That is the nearest number that I get, which is less than or equal to 867. So I'm going to multiply by 3. 5 into 3 is 15. 5 into 3 is 15. 1 16. 6 plus 1 7. 765. So 3 times is 765. So on multiplying 255 and 3, you get 765. What is remaining out of 867? 867 minus 765. 7 minus 5 is 2, 0, 1. So the remainder is 102 in this case. So now I need to apply Euclid's division lemma to these two numbers. This is B and this is R. So in the next case, this becomes A and this becomes B. 255 comes here, is equal to 102 into something plus something. I need to enter again now. Seeing this is approximately 100 and this is 200 plus. So maximum of 2 can be multiplied. So 102 into 2 is 204. 255 minus 204 gives 151. 51 is remaining as a remainder. Here again some remainder is remaining. So again you need to apply the Euclid's division lemma for these two numbers. So now we need to write 102 is equal to 51 into something plus something. So just by seeing I can find out that 51 into 2 is equal to 102 and the remainder is 0. That means that 51, that is the divisor at this stage, is the highest common factor of 867 and 255. That is, therefore 51 is equal to the HCF of 867 and 255. Yes? Now this is a question from the examples. You need to show that any positive odd integer is of the form 4q plus 1, 4q plus 1 or 4q plus 3 for some integer q. So q is something else. So I think q should be the quotient. So as we have learned only Euclid's division lemma, I am going to use that now. So let a be any positive integer. A is any positive integer. Yeah, a is any positive integer now. So applying Euclid's division lemma, to, you need to apply this to a and 4. So I am applying to a and 4 just because I can see a 4 here. So I need the divisor to be 4 in the case. Hence using Euclid's division lemma to a and 4, you can find that a is equal to 4q plus r, where R can be 0, 1, 2, 3. There are 4 cases now. So first we'll take these 2 cases together. So what do we get? Cases 1 and 3. A is equal to 4Q and A is equal to 4Q plus 2. That is 2 into 2Q and A is equal to 2 into 2Q plus 1. Therefore, these integers are even. As 2 is a factor of these, that means that these integers should be even. Now we are going to consider the cases 2 and case 4, where R is equal to 1 and R is equal to 3. So A is equal to 4Q plus 1 and A is equal to 4Q plus 3. Hence, are odd. Therefore, we can conclude that the given statement is correct. That is, any positive odd integer is of the form 4Q plus 1 or 4Q plus 2. If it's not of that, it is not of that form. That means that they are even. That's why they need to be in that form itself. That is 4Q plus 1 or 4Q plus 3. We have the next question now. It states that you need to show that the square of any positive integer is of the form 3m or 3m plus 1 for some integer m. So it's any positive integer, you should show that it's a multiple of 3 or multiple of 3 plus 1. So Euclid's division lemma, that is the same thing. Let A be any positive integer. It is given positive integer, so you need to write that it's a positive integer. So A is any positive integer now. Now you are going to applying Euclid's division lemma. That is what we have learned. Euclid's division lemma. For which two numbers? For A. A is one thing, and what is the other one? Seeing this, I can find out that it is some multiple of 3. So I need to get A as therefore B should be 3 now. A should be a multiple of 3 only. So applying Euclid division lemma to A and 3, you can get that A is equal to 3Q plus R, where R can be 0, 1, 2. In case 1, where R is equal to 0. R is equal to 0, that implies this is not there. So A is equal to 3Q. Square of that integer, that is A square, is equal to 9Q square. That is equal to, I need to get it in terms of 3. So 3 into 3Q square, I'll group this term and I'll name this as M. That is 3M for some integer M. In case 2, R is equal to 1. That is the second case. There, if R is equal to 1, A is equal to 3Q plus 1. A is equal to 3Q plus 1. So what will be A square? A square is equal to 3Q plus 1 whole square. That is equal to, you're going to use the A plus B whole square formula. That is A square. 3Q whole square is 9Q square plus 2AB. 2 into 3Q into 1 or 6Q. 6Q plus 1 square is 1. So I feel that it's going to come in this format because there is 1 here. That's why. So I'm going to take 3 outside from these two terms. So 3, if I take it outside, you get 3Q square plus 2Q plus 1. That is, I'm going to write this in terms of as a M itself. This whole term is M. So it is 3M plus 1. for some integer m. What will be the case? Third case, where r is equal to 2. That means that a is equal to 3q plus 2. Here in place of r, we are going to write 2. That's why it is 3q plus 2. A square is equal to 3q plus 1 whole square. So we are going to simplify this using a plus b whole square formula. That is, similar terms you get. This is 3q plus 2 itself. Okay, so 9q square plus 2 into 2 into 3, that is 12. 12q plus 2 square is 4. So there is a 4 here. Hence, I need to get this in terms of this or this. But I feel that 4 can be written as 3 plus 1. So I'm going to rub it and write it as 3 plus 1 now. 3 plus 1. So 1 I can get in this format. So I'm going to take 3 from this term. So 3 into 3q square plus 4q plus 1 outside. This whole term I am going to write it as m now. That is 3m plus 1 for some integer m. So in all the three cases you have found out that the square of this any positive integer, maybe whether the r is equal to 0, it forms 3m, and whether if the remainder is 1 or 2, it forms the 3m plus 1 format. That means that the square of any positive integer is of the form 3m or 3m plus 1 for some integer m. The next question is, show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8 for some integer m. So this is similar question as the previous one, but this is a 9. So I should check whether I can use 3 itself because it's a cube number. So let a be any positive integer. Write as short form positive integer. Then need to use Euclid's division lemma. Euclid's division lemma for a and 3. So this is a shorter one. Instead of using here 9, you'll get 9 cases. If you use 3, you'll get only 3 cases, and each one will be one of those cases. So if you use 9 as given in the textbook solutions, you are going to get 9 different cases, but the answer is going to come to be the same. So it is better to use a shorter option. So in applying Euclid's division lemma for a and 3, you can find out that a is equal to 3q plus r, where r can be 0, 1, 2, 3. 1, 2 itself. Yeah, 3 cannot be the case. So in the first case, I'm going to do it a little bit faster because the previous question was the same. Here, when r is equal to 0, a is equal to 3q. From this you can show that a cube is equal to 3q whole cube. 3q whole cube, q I write it as q cube itself. What is 3 cube? 3 into 3 into 3. 3 into 3 is 9, 9 into 3 is 27. 27 q cube. Now I want it in the form 9m, 9m plus 1 or 9m plus 8. So there is no extra integer to use 8 or 1. So this is 9m itself. So I need to take 9 outside. So 9 into 3 q cube. 3q cube is one together term, and I'm going to write it as some m for some integer m. Second case, r is equal to 1, where then a is equal to 3q plus 1. That means a cube is equal to 3q plus 1 whole cube. So you need to use a cube plus b cube formula. Let me write that here. This is just for your knowledge. A plus b whole cube formula that needs to be a cube plus 3ab into a plus b plus b cube. For me this form is enough for this question. Otherwise you need to use the expanded form where 3a square b plus 3ab square comes up. So I'm just using this 3 cube whole cube, that is the same one, 27 cube you are going to get, that is the a cube, then 3ab, 3 into a is 3 cube into 1 let it be, then a plus b is as it is, 3 cube plus 1 whole cube is 1. So 1 is the extra integer you are going to get in this, so it goes to this format, this is 9m plus 1. So I need to take 9 outside now. From 27 I am going to take 9 outside. You get 3 cube. Then you are going to get this 3 into 3 is 9. So plus q into 3 cube plus 1. I leave it as it is. There is no use of simplifying that also. I am going to just write it as m. So 9 I am going to take it out. It comes to be q into 3 cube plus 1 plus 1. So this whole thing I am going to write it as sum m, 9m plus 1 for some integer m. In the third case r is equal to 2, where a is equal to 3 cube plus 2. Therefore a cube is equal to 3 cube plus 2 whole cube. Similar you get here 3 cube whole cube is 27 cube plus here you will have a different one, 3 into a is 3 cube itself, 3 cube into 2 into a plus b is 3 cube plus 2 plus 2 cube is 8. So you got an 8, there is no worry now, 8 is here. And again now we are going to take 9 outside, so this becomes 9 into 3 cube plus again 9 from here, 2q is outside and 3q plus 2 is inside. I'm not going to simplify this, let it be as it is. I'm going to write whole this term is, and there is also plus 8, right? Plus 8, whole of this term is m, so this becomes 9m plus 8 for some integer m. So by these three cases you can find out that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8 for some integer m. Yeah, this is a question from the exercise, that is question number 3 from exercise 1.1. This is a simple question, but it looks a very big and so much things in that. The army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same number of columns. What is the maximum number of columns in which they can march? So there are so many people, so maybe 616 people here, and this should be the same column of this. Same number of columns for the band people as well as the army people to march. So for this you need to find the highest common factor of 616 and 32 so that you can have a proper rectangle. Otherwise it's not possible for them. Maybe some people are extra while doing that. So for this you need to find the HCF of 616 and 32. For finding the HCF of 616 and 32, we are going to use the Euclid's division lemma. So what is Euclid's division lemma here? 616 is equal to 32 into something plus something. So how we are going to use this? So 32 can be somewhat here by seeing this mostly we found that 32 is now 616 is not divisible by 32. You need to get a reminder. So maybe the double of yeah, 640. There's a number that's coming to my mind now. So 32 into 20 is 640. But 640 is more than 616. I need to get a number that is less than 616. So I'll subtract 616 from this. Oh, sorry. Yeah, I need to subtract 32 from this so that I get a proper number here. Here it becomes 8, 608. So 608 is divisible by 32. That is 32 into 19. So I should be 19 here. And what is remaining is 616 minus 608. That is 8. 8 is extra. Now we are going to apply Euclid division lemma for 32 and 8. 32 is equal to 8 into. So however, by multiplication tables, I know that 8 into 4 is 32 and the remainder comes to be 0 here. Therefore 8 is the HCF of 616 and 32. That means that the maximum number of columns in which the army contingent and the army band should go is 8. Yeah, there is one more similar question. You need to show that x square minus x is divisible by 2 for all positive integers x. So here let x be the positive integer that is already given. Applying Euclid's division lemma to we are applying Euclid's division lemma to x and 2. We are going to have 2 here so that I get only 2 cases. From this you can find that x is equal to 2q plus r, where r is 0 or 1. In first case, r is equal to 0, that means x is equal to 2q, or you need to find x square minus x here. X square minus x is equal to 2q whole square minus 2q. From here you can get 2 common, that is 4q square minus 2q, or 2 common, 2q square minus q. Therefore this is divisible by 2, or it is a multiple of 2. In the second case, r is equal to 1, x is equal to 2q plus 1. This is r is equal to 1, that's why. Therefore x square minus x is equal to 2q plus 1 whole square minus 2q plus 1. 2q plus 1 whole square is 4q square plus 4q plus 1 minus 2q minus 1. Plus 1 minus 1 is cancelled. 4q square plus 2q. We are going to take 2 common outside, that is 2q square plus q. Therefore it is divisible by 2. Therefore in both the cases you can find out that x square minus x is divisible by 2. So whatever be the positive integer x square minus x will be divisible by 2 is what the conclusion we are going to get. Thank you.